Hi, my name is Mandeep and I'm presenting my term project LMS Adaptive FIR filter that I have taken under Professor Changchu at San Jose State. Today's topics are let's have a look at brief introduction, the block diagrams and the design modules in my design, the parameter sizes and the simulation results in MATLAB as well as ModelSim, and the conclusion. The objective of the project is to design a least mean square adaptive filter engine to reduce the noise or echo cancellation. In general, the filter is defined as convolution of signal to noise. X of n is the signal plus noise, that is the input signal, convoluted with the filter coefficients. So we get the y of n, which is the filtered output. For the project, we need to design an LMS algorithm that adapts based on the input noise and gives us a adaptive coefficient, which is hk of n plus 1. So this is the LMS algorithm. Using this algorithm, we are going to design our filter engine today. So this is the block diagram of our design. We get the desired signal and the signal plus noise, which is x of n, from the MATLAB code. This desired signal d of n is then d of n is basically a noise-free signal, so that is pipelined 25 stages, and the noise plus signal plus noise is sent through the MAC unit, which is nothing but an FIR filter with the default coefficients h of n. So as my MAC unit is a 24 tap filter, I have to pipeline my desired signal to 25 stages. I added an extra stage after a MAC. So it goes into a subtractor, which is a floating point subtractor, and it gives me an error signal, which is dn minus yn. So this is sent to the LMS algorithm block. As shown in the previous slide, we require an error signal such that new coefficients are adapted. So by the time my E of n error signal reaches my LMS algorithm block, it takes almost MAC unit consumes 24 clock cycles, and I have 25 clock cycles, and I have three pipelines in my subtractor. So that's a total of 28 stages. So I have to pipeline my x of n 28 stages and feed it to LMS algorithm block. The LMS algorithm block calculates my new adapted coefficients, that is hk of n, and it is sent through the multiplexer. Now the multiplexer sends to the MAC unit the new adapted coefficients such that my y of n is an error-free noise signal. So this is the LMS algorithm block diagram. So we get the pipeline signal plus noise, that is x of n, and error signal e of n, which goes into a multiplier. So this is my adaptive coefficients equation. So the error signal is d of n minus x of n is fed to a multiplier where error signal and my signal plus noise is multiplied together, and it is shifted with a step factor of I beta. So I beta is in the powers of 2. So shifting operation is equal to the division of the I beta. So after calculating, after multiplying, so it is sent to the floating point adder where my old filter coefficients gets added in the floating point adder and gives me my new adaptive coefficients. So my modules used in the design are FIR filter. FIR filter is basically a multiplier and an accumulator, a MAC unit. So my signal gets in, and here it is multiplied with my old coefficients, and this is a delay unit where basically my signal that is fed first is delayed by a delay unit and later is multiplied with the next coefficient and so on. So it is nothing but a multiply and an accumulate. So finally I get my y of z. So I used the alter as IP the MAC IP in my design. And the next module would be dual port RAM. So I use this dual port RAM so that it can read and write the memory cell simultaneously at different times, as I'm getting my signal plus noise, which is X of n, and my desired signal D of n from the MATLAB. I store them in the RAM so that my dual port RAM can access those values at any instant of time. And I use the Altera's dual port IP, as you can see here, for my dual port RAM. And the next module would be a floating point multiplier block. So in this block, when we get two input signals, it checks for the difference in the exponent signal, and then it normalizes the decimal point such that we can multiply both the signals, and XOR is used to judge the resultant sign of the result. So the parameters I've used here are data in, which is the X of n signal, the signal plus a noise, which is a 32-bit signal, and my desired in, which is D of n, and my old coefficients are H of n, which are also 32-bit. The new adapted coefficients are Hk of n, and my error signal E of n, which is 32 bits. So I used a step size I beta of 8, which is mu, which is equal to 0.125. So these are my MATLAB simulation results. So this is my the bottom one is my signal plus noise, which is X of n. When fed through to the LMS adaptive filter, this is the final output, which is noise free signal that I have attained. So let's look into the model simulation results as well. So yeah, these are my model simulation results. This is my input signal X of n, and as you can see, this is the desired signal, which is noise free. So here you can see a difference in error signal has been converged over the time. It has been converged to almost with a zero error at almost 3,300 picoseconds. So my LMS adaptive filter has adapted over time and had tried to converge the error signal, that is a difference between the desired as well as the input X of n signal, such that there is a clear output without any noise. So these are my MATLAB simulations with different tap lengths for my LMS adaptive filter. So as you can see, this is an simulation result of 8-tap filter, and this is a 16, and this is a 24-tap filter, and this is the result of 32-tap filter. We can see that when the tap length is 8, the noise had almost converged around 680 timestamp on the time scale, but yet it's not completely zero. Coming to the 16-tap filter, the convergence of the noise is attained around 522 timestamp. At the 24-tap filter, we get it at 480 timestamp, and at 32-tap filter, the noise signal has converged at 290 timestamp. So as you can see here, the noise has converged a bit quicker than the lesser tap filters. So as you increase the number of taps, the convergence rate has also increased, and you get a clear noise free signal earlier. So here I conclude that with difference in tap lengths in the FIR filter, we can achieve an convergence of the error signal earlier. As you increase the tap length, the convergence rate of the error signal is faster, and we can also change the step size, which is a mu, such that the rate of convergence can also be made either faster or slower. For the future scope, we can extend this implementation physically over an FPGA board. On an FPGA board, and we could simulate a real-time scenario where you can input an audio signal with noise, and using our design engine, we can if we could generate a noise-free signal. We can generate a noise-free signal over a real-time FPGA board. So that is with the future scope. If possible, I would like to make a video of the implementation over an FPGA. All right, thank you.